So one of the ways that you can help students be more successful with inquiry in the laboratory is to not only introduce inquiry in the laboratory. Don't limit inquiry to lab. If you're using questioning techniques during the demonstrations that you do in class, or if you're using active learning techniques in the classroom, then students are already building their independent learning and problem-solving skills. This will make the laboratory go much more smoothly when students learn that they can solve problems for themselves and that they can troubleshoot it when something goes wrong. I think that part of something that's arisen in our very test-driven culture is that students can sometimes gain a bit of learned helplessness. They sometimes think that the teacher must give them every bit of information and that they should never be able to figure out something for themselves. And I feel like we do a disservice to students if we always give them the answer to everything instead of encouraging them to think for themselves. Certainly, if students get stuck, help them out, guide them, point them in the right direction. But we should avoid always giving the answer before they've had a chance to think it through for themselves. The more questioning that you can do with your students, the more that you can ask them, how do you know? The more deeply they are going to have to think about what they do know and how they can justify their understanding with data, either from laboratory or from published data sources. And questioning does not need to be limited to the laboratory. When you do a demonstration for the class, have students ask questions about what they just saw. They're likely going to ask why questions, and that's fine, but try to steer them into the direction of what would happen if, or would it work the same way if we substituted this, or is there another way to do this same experiment? These are questions that could be verified or refuted experimentally. Also, you're under no obligation to answer every one of the questions that the students pose. It's an exercise to get them poised and able to ask scientific questions, both in the present moment and in future times that you want to call on that skill. I'm fortunate that in my room, the chemical storeroom connects directly to the back of my classroom. So if I'm doing a demonstration or we're in a lab experiment and students ask an interesting question, and if I have equipment and the chemicals to test it, I can just walk to the back of the room, get the supplies, and show them right then and there what happens. If you don't have that luxury, then and a great question comes up as part of a class discussion, just say to your students, you know, that's an awesome question. I'm going to try that out first thing next class period, and then grab the materials after school and have it ready to go for tomorrow. The more you can do to encourage the curiosity of your students, the better off they're going to be. I've run into so many people in casual conversations at parties or gatherings with friends who say that science wasn't their thing because they were creative, as if science was the antithesis of creativity. And I think part of the reason why that misconception exists is that many textbooks focus so much on presenting theory as historical fact, like this is what it is and there's no questioning it, rather than giving kids a pathway of looking at experimental results, looking at data, making conclusions for themselves, and then framing some terminology to explain the phenomena that they just saw. You can counter this a little bit in your instruction if you just show students fascinating phenomena first, and then work to build the understanding in the lesson that follows. It also never hurts to come back to the same demonstration after you've discussed the concept. That way students can analyze what's going on with the new knowledge. They're not worried about being fascinated by it. They can actually apply, oh, this is what I just learned, and yeah, I can see how that actually makes this demonstration work. And then you can also ask questions to get kids to extend that knowledge and frame it and extending it into new contexts that they can investigate later. So if we want students to be independent thinkers in the laboratory, it's important to develop their reasoning skills throughout the course, not just in the laboratory. There are a multitude of excellent sources for inquiry-based activities that can be used in class settings where students are working with data and models and where they can develop an understanding of concepts in the curriculum by using concrete data points and manipulative models. The POGIL project is one source, as is the Target Inquiry Program that was originated at Grand Valley State University. John Gelder out of Oklahoma State University has built several computer animations and guided or structured inquiry activities that accompany them on the molecular level laboratory experiments. And Ton Greenbow's group at Iowa State University has done similar animations with structured inquiry activities. With so many of the new computer animations and models available, there are a number of excellent activities where students can manipulate variables in a system and observe the result. Sites like PhET and Molecular Workbench and the Chem Collective all do this. Links to these sites are in the notes that accompany this video, so you can check them out on your own time. Using these molecular level simulations, though, students can use data to find relationships between variables with no equipment set up other than turning on a computer. These activities can be done at home with a set of guiding questions, or they can be done in the classroom in collaborative groups. All of them allow a concrete example where students can start to explore relationships between variables before coming to class, and then we can use the class time to have an informed discussion. Imagine how much better you could teach if students walked into your classroom, for example, already knowing the relationships between the gas variables of pressure, volume, temperature, and number of particles. And they already had a visual model in their minds of the changes in molecular speed that occur when the variables in those gas variables are changed. I know that when I think of chemistry, I see a delicate dance of atoms and molecules in my head, but our students don't walk into our classroom seeing the same thing. These simulations and animations can help greatly to build students' understanding of the molecular world, as well as prime them to have really meaningful discussions in class. The point of inquiry is to get students to think and reason for themselves, to not always rely on a teacher or an authority figure to give them the right answer. And if we're going to build a scientifically literate society, we really need to encourage students to examine data for themselves, to come to reasonable conclusions, and to be able to support that conclusion. That is essential to the furthering of our society, but also for us training the next generation of scientists. And I absolutely believe that inquiry methods can help that happen better for our students.